All right, so this is your Big Idea 6 review question. So these are frequently asked questions that you guys had. So I'm going to go through and answer them. The first question was asking if I could go over the steps for determining the pH when an acid and a base are mixed together. And so the question that you have to ask yourself in order to answer this question is what exactly is left over? When I add an acid and base together, they're going to react. What is going to be left over, and that will dictate what my pH will be of my final solution. So if you have a strong base or a strong acid left over, then it's pretty easy because a strong base, which is OH minus, or a strong acid, which is H plus or H3O plus, you can just plug in their concentrations to your pH or pOH formula to determine the pH. But the question becomes, how do I determine what's left over? How would I know if it's a strong base or a strong acid left over? Well, we're going to do a problem. So here I'm told my volume and my concentration of my strong base, my volume and my concentration of my weak acid. So I'm going to show the reaction that occurs between them. So I've got acetic acid reacting with my strong base, so I'm just going to write it as OH minus. Now there was also a question about double versus single arrows for here. Remember, if you have a strong base or a strong acid reacting with a weak acid or a weak base, it's going to react completely. It's going to go to completion. And so I represent that with a single arrow. If it were a weak acid dissociating or a weak base dissociating or any other reaction that's in equilibrium, you would show a double arrow. That being said, it's never wrong to show a double arrow because a double arrow ultimately says that it will reach equilibrium. It doesn't say what's going to be favored. So if you always put a double arrow, it won't be wrong. I like to put a single arrow because that shows me that all of one of these is going to react, and that's why I put it. Okay, so I'm going to put my other product. I'm going to put my products, acetate and water. Okay, so in order to figure out what's left over, I need to create an ice chart. So I'm going to do that. Now, another question came up with regards to how do I know when I need to figure out new concentrations? Would I use 0.20 and 0.10 for the concentrations that I plug into the ice chart? And the answer is no. As soon as you add two solutions together, regardless of whether their volumes are the same or not, that's going to change the concentration of those solutions because initially the volume of the sodium hydroxide was 50 mils, and its concentration was 0.2. Well, if I add it to acetic acid, its new volume is going to be 100 mils, and so that's going to actually alter its concentration. It's going to decrease its concentration. So that's when you need to use the formula M1V1 equals M2V2. Okay, that's the only time you use that. You do not use M1V1 equals M2V2 when you're doing a titration problem. For titration problems, you're going to be using stoichiometry. So I'm going to take 0.2 multiply by 50, divide by the total new volume, which is going to be 100. And so for the concentration of hydroxide, I get 0.100. For the concentration of acetic acid, I do the same thing, but with 0.1 molar, so I get 0.050. My initial concentration of acetate is 0. So this is going to react completely. So it's going to change by 0.05. And what you should notice is that I have strong base left over. Yes, I do have the weak base as well, right, my acetate ion, but ultimately this hydroxide, that will dictate what my pH is. So it's very nice because all I have to do, since I have strong base left over, I just have to plug this into my pOH formula. Okay, and so the pOH that I get is 1.30. So to determine the pH, 14 minus that value, and I get 12.70. Okay, so ultimately, how do I figure out what's left over? You gotta first create an ice chart. Okay, so let's look at another example. What if instead of a strong acid or strong base being left over, I have a weak acid and a weak base that's left over? Okay, so let's actually look at that to see what that would look like. So in the problem, it tells me, give me one sec to straighten that. Okay, calculate the pH when 30 mils of 0.250 molar NaOH reacts with 0.20 molar of HA to reach a final volume of 80 mils. And so this was actually from a quiz. This was from your 6.10 quiz, letter F. A lot of people asked about that question. So I'm actually just doing the problem in my explanation here. So if I have 30 mils of NaOH and an 80 mil total final volume, what that tells me is that I actually used 50 mils of HA, okay? Just additive, right? So what I'm going to do is I'm going to show, because I want to figure out what's left over, I'm going to show my reaction. So my weak acid will react with my strong base, and it will form single arrow because it's going to react completely. It's going to form water and A minus. Okay, so for this guy, the concentration of HA, don't put 0.20. I know you might be tempted, but keep in mind I'm adding two different solutions together, so I've got to find the new concentration. So it'll be 0.2 times 50 divided by the total volume, which would be 80 in that case. And so what I got for this was 0.125. When I did that for hydroxide, 0.25 times 30 divided by 80, I got 0.09375. The initial of A minus is 0, and so when these react completely, it's going to change by 0.09375. And we're going to add that. And so what I end up with at equilibrium, or when I'm done at my end, is the following. So notice, to answer the question, what is left over, I have weak acid and I have weak base, which tells me as soon as I have weak acid and weak base, you should be thinking, thank goodness, because what that tells me is I can use my Henderson-Hasselbalch equation. So pH equals pKa plus the log of your weak base divided by your weak acid concentration, okay? My Ka for this problem, I think it was given to you in the problem. I'm sorry, I didn't write it down. But we know that the concentration of the base is 0.09375. The concentration of the acid is 0.0313. And so you can just plug it in there, and I get 4.68. So that was from a quiz question, an old AP question. Okay, all right, well, what if instead I have a weak base or a weak acid? I don't have a weak base and a weak acid. So let's say, for example, I end up with just a weak base. These are the ones where it is slightly more work, because ultimately, if you just have a weak base or a weak acid, what that tells you is you're actually at your equivalence point. So let me show you how you would know that. So for this one, it tells me my volume and my concentration of my weak acid, my volume, my concentration of my strong base. Again, this was from a question, this was from number 14 from your review for this big idea, okay? So I'm gonna write out my reaction to figure out what's left over, because even though I told you, or sort of told you, I wanna show you how you would know. So let's write out our reaction. Again, I'm adding two different solutions together, so I need to find their new concentrations, okay? So 0.2 times 40 divided by the total volume, which would be 93.3, and the concentration I got for acetic acid was 0.0857. Okay, same thing for hydroxide, 0.150 times 53.3 divided by the total volume, 93.3, and I got 0.0857, which means I have equal concentrations of my acid and my base, which immediately you should recognize means that I'm at my equivalence point. I've got equal amounts of acid and base. So my change will be 0.08, sorry, that should be a 7. And so what I realize is that when I'm done, I only have my weak base because I don't have any of my weak acid or strong base left over. I cannot use my Henderson-Hasselbalch equation here because I don't have any weak acid. And so what I know is I have a base, and this question now becomes, if I have that concentration of base, what would my pH be? Well, if you know the concentration of your base, to determine your pH, I have to do a weak base dissociation reaction now. So I have to create a whole nother ice chart. And the reason why it's a weak base dissociation is because, well, I have a weak base. So if I had told you completely separate from this problem, hey, my concentration of this weak base is this, what's the pH? You would have done a weak base dissociation reaction. Okay. So I'm going to create a second ice chart. That's why these are slightly more painful, but it's fine. I don't have any weak acid or strong base. This is a weak base, so my change is going to be X. Okay, so now to solve this, I need to write out my base dissociation expression. But the issue with this problem is that I give you your Ka value. I don't give you your Kb value. So you need to take 10 to the negative 14th, because remember, Ka times Kb equals 10 to the negative 14th. So then I need to take 10 to the negative 14th and divide by my Ka. So the Kb you get, which you're going to use, is going to be 5.6 times 10 to the negative 10th. Okay, times, which equals x squared divided by 0.0857 minus x. I'm going to get rid of that x because I'm assuming the rule of 100 applies, which tells me the initial concentration, 857, divided by my Kb is going to be a lot larger than 100. Okay, and now I can solve. So the x that I got was 6.9 times 10 to the negative 6 molar. So that's my concentration of hydroxide, which would then give me my pOH if I took the negative log of it, and I got 5.16. So to determine the pH, 14 minus that, and I get 8.84 for my final answer. Okay, so ultimately for all of these questions, guys, it is a matter of what is left over and figuring that out by using an ice chart. If you have a strong base or a strong acid left over, you can just easily plug it in, the concentration that's left over, to figure out pH. If you have weak base and weak acid left over, like we did with this one, then you use Henderson-Hasselbalch. If you have a weak base left over, you're going to have to do a second ice chart. If you had a weak acid left over, you would do a weak acid dissociation reaction and figure out your pH. All right. Let's look at the next problem. So the next question was, how does a common ion effect affect solubility? Okay, so my best way of explaining this is by showing you with a problem. Okay, so when we're talking about solubility, we actually have to write out our dissociation reaction. So we're dealing with LaF3, so it's going to break apart into La3 plus and 3 fluoride ions. Okay, so I know my KSP value. Keep in mind I'm going to want to use an ice chart. Okay, so I don't have any of either of these present, so it's going to be plus x plus 3x because there's a 3 coefficient. And so when I'm solving for my KSP, or when I put in my KSP expression, it's going to be 2.0 times 10 to the negative 19th equals x times 3x cubed, which would be 27x cubed times x, so that would be 27x to the 4th. So when you solve for x, the concentration that you get is 9.3 times 10 to the negative 6. So all I did here was said, hey, when I have a saturated solution of LaF3, what would the concentration of La3 plus be, for example? Okay, so that's going to be the solubility of it. So that much is going to dissolve. If I wanted the concentration of F minus, I would then just multiply by 3. But this, regardless of what situation you're in, regardless of what volume you have, This is the most that can dissolve. That is the solubility, that's your X, of that solution when it is saturated. Here's the issue. Notice I start with 0 of La3 plus and F minus. What if that isn't the case? If that isn't the case, if I actually start with one of these, then I have a situation which is the common ion effect, meaning that the ion already exists in solution. So here I start off with some Kf. Well, obviously K has nothing to do with this reaction because K isn't in La, or at F3. However, the F minus is in your original dissociation reaction. It's right there. So instead of starting with 0 of F minus, when I do this, all this will be the same. I don't have any La3 plus, but I do have F minus now. I have 0.010 molar. Now, a quick question might be, why don't I find a new concentration? That's simply because I didn't tell you the volume that I'm adding, so we're assuming that the concentration isn't changed by having F minus in solution already. Okay, so same thing here, plus X plus 3X. So when I write my equilibrium expression, which is still, the value for KSP is still 2 times 10 to the negative 19th, it's going to be X times that. Okay. Now, the awesome thing as far as solving for X is concerned is because the initial concentration, 0.010, divided by my KSP, which is 2 times 10 to the negative 19th, since that is definitely bigger than 100, what I can do is get rid of any plus or minus X, so I can get rid of this. So all I have to do now is take 0.01, cube it, and then divide 2 times 10 to the negative 19th by that value. And so the X value that I get now is 2.0 times 10 to the negative 13th molar. So let's compare and talk about the common ion effect. When I had no La3 plus or F minus in solution, the solubility of this solution was 9.3 times 10 to the negative 6, meaning that concentration of La3 plus was in solution and 3 times that was present for F minus. When I started with F minus, a common ion, that caused the solubility to decrease from 10 to the negative 6 to 10 to the negative 13th, which means when we're talking about the common ion effect, if you have a common ion, it significantly reduces the solubility. Okay, and you can see that in the values, right? Because if this is already present, not as much can actually dissolve because you already have some of it present, so it prevents it from actually being able to dissolve as well. So let's talk about a more conceptual question with respect to the common ion effect. So it says, which of the following solutions would zinc iodate be the least soluble in? So I'm going to really quickly write out the dissociation reaction for zinc iodate. Okay, so if you look at this, I want to find something that is the least soluble, meaning I want a common ion. So if you look, barium and chloride. Barium and chloride are not present, so that doesn't work. Sodium and iodate. Sodium's not here, but iodate is. So that would be a common ion. Okay? Potassium and carbonate, neither of those is present. And then pure water. Well, pure water would actually cause more to dissolve, so that would actually cause it to be more soluble. So sodium iodate would be your answer because it contributes a common ion, which is iodate. All right, for the next question, people ask, how can you determine if a precipitate forms? So let's actually look at zinc iodate really quickly to talk about that. So if I'm asking, will a precipitate form, what you do is you actually need to calculate your Q. Okay? So when you calculate your Q, if the Q value you get, because you are not yet, basically it's saying, I'm not at equilibrium, or I'm not sure if I'm at equilibrium. If Q equals your KSP, what that tells you is that you have a saturated solution. meaning it is in equilibrium. You're not going to form a precipitate. Already the maximum number of ions that could dissolve have dissolved. So in this case, for LAF3, for example, I have my Q equals my KSP. I have the maximum amount of ions that are dissolved. Okay? If I add more La3+, if I add more than 9.3 times 10 to the negative 6, it's going to cause my Q value, because remember Q is products over reactants, it's going to cause my Q to be larger than my KSP, right? Because I'm adding more product, I'm adding more to the numerator. So if my Q is greater than my KSP, that actually causes a precipitate to form, because it's going to cause my reaction to proceed in both cases here. It's going to proceed to the product, or to the reactants, and the reactants are both solids. So if your Q is greater than your KSP, then that's going to cause a precipitate to form. If your Q is less than your KSP, it does not form, because it would shift to the products, and the products are simply just going to be your ions. Okay, so if Q equals KSP, whatever your X values are, that is the maximum solubility. That's the maximum amount of ions you can dissolve in solution and be in equilibrium. If you try and add any more, that would cause your Q to be too big, and it would cause a solid to form, right? If, for example, you added water, that would cause, and I'll get into this in more detail in a little bit, that would cause your Q to be less than your KSP, shifting it to the right, and therefore causing no precipitate to form. Okay. The next question asks about selective precipitation. So I'm going to show an example problem. The whole point of selective precipitation is, all right, I have 2 anions here, and I have specific amounts of those anions. And I want to figure out which of those is going to precipitate out first. Okay? Well, the issue is you first have to write out your dissolution reaction. So if I'm adding barium nitrate, obviously nitrate's not going to have anything to do with it because it is always soluble. So in this case, barium would form an ionic compound with fluoride, or barium could form an ionic compound with sulfate. So I'm going to show both of those dissociation reactions. I'm first going to show barium sulfate. And then I'm going to show barium fluoride. Okay. And then I know that when my Q equals my K, I am in equilibrium. So if I want a precipitate to form, I actually want my Q to be greater than my KSP. So basically what I'm going to do for this problem is I'm going to solve it to figure out what concentration of barium would be required for each of these to reach a value where Q equals my KSP. Any amount above that and a precipitate will form. Well, how do I do that? Well, I know that my Q is going to be my concentration of barium ions times my concentration of sulfate. For this one, Q equals my concentration of barium ions again, times my concentration of fluoride ions, squared because it has a coefficient of 2. Now, I know my initial concentrations because I have 1 liter and then it tells me my number of moles. So I'm trying to solve for whatever concentration of barium would be needed for my Q to equal my KSP. So I'm going to just plug in Ba2 plus right there. And then I know my concentration of sulfate that I have. It's 0.20. Well, what is my KSP value for barium sulfate? I believe it is given to you in the problem. I don't think I included it for some reason here, but for barium sulfate, your KSP value is 1.1 times 10 to the negative 10th. So when I solve for the concentration of barium that would be required for my Q to equal my KSP, I get 5.5 times 10 to the negative 10th molar. When I do the same thing for barium fluoride, my KSP is 1.7 times 10 to the negative 6. That's just given to you. I'm solving for the concentration of barium that would be required, and the concentration of fluoride is 0.04. And so the concentration of barium that I get is 1.1 times 10 to the negative 3rd molar. All right, what do these values tell me? What this tells me is when I have a concentration of 5.5 times 10 to the negative 10th molar, I have a saturated solution for barium sulfate. When I have a concentration of 1.1 times 10 to the negative 3rd molar for barium fluoride, I have a saturated solution. Anything above that, and my Q, I'm no longer in equilibrium, and my Q will be greater than my KSP, meaning a precipitate will form. So if you think about it, I literally start off with just sulfate and fluoride, and then I slowly, drip by drop, add barium ions. So what you're looking for, the solid that's going to precipitate first is the one that requires less barium ions, because as you're slowly adding barium, whichever one requires less barium is the one that'll precipitate out first. So barium sulfate is going to precipitate out first. And if I said what concentration of barium is necessary to cause a precipitation, any value above 5.5 times 10 to the negative 10th will cause barium ions to precipitate out of solution. Okay? So that's selective precipitation. Next question, how can you determine if a salt will act as an acid or a base? So the question that you really need to ask yourself is, where is the salt coming from? Because remember, a salt comes from, you have a cation and an anion. Okay? The cation actually comes from a base, while the anion comes from an acid. So I'm going to show you some examples to explain why. But if the cation, which came from a base, came from a weak base, then it can act like an acid. If it came from a strong base, it's not going to act as an acid, because remember, the conjugate of a strong base is not acidic. The conjugate acid of a weak base is acidic. Remember, the stronger your base, the weaker its conjugate acid is. Here, if the anion came from a weak acid, it will act as a base. If it came from a strong acid, it will not act like a base. So I always think A followed by B, right? If this came from something that was strong, it won't act as an acid, but if it came from something weak, it'll act like an acid. If this came from something weak, it will act like a base. So let me show you some examples. So these are problems that you guys had on a quiz. Which of the following will have the lowest pH? So I'm going to look at each of them and figure out, if it is a salt, would it act like an acid or a base? So NaBr. Na is Na+, and the base it came from is NaOH. That's where the Na+ came from. Well, that is a strong base, so that cannot act like an acid. Br came from HBr, which is a strong acid. So that cannot act like a base, and therefore this is actually going to be a neutral salt. NaOH, they tricked you, it's not a salt, it's actually just a straight base. Okay? NaC2H3O2. So Na, again, came from NaOH, which is a strong base. C2H3O2 minus came from acetic acid, which is a weak acid, which means that acetate ions can act like a base. So this is going to actually act as a base. Okay? NH4Br. NH4 came from NH4OH, which is a weak base, which means that this can act like an acid. Br came from HBr, which is a strong acid, so it will not act like a base. So this is going to act like a base, this will act like an acid. All right, well, what exactly does that mean? Well, if NaC2H3O2 can act like a base, again, I ignore the Na+, because that doesn't affect my P, it doesn't affect my solution at all, it doesn't affect my pH because it's neutral. So I've got a weak base. So how would I figure out the pH of this? I'm just going to set this up. Since this is a weak base, I'm just going to write out a weak base dissociation reaction. Then you'd create an ice chart, plug in your initial concentration, and you'd call it a day. For NH4Br, since NH4 plus will act like an acid, you're going to do a weak acid dissociation reaction. So H plus and NH3. Or you could write this with water if you wanted to. Either way, that's what happens. Let's look at the second example. I give you KClO4. So potassium came from KOH, which is a strong base, so that cannot act like an acid. ClO4 came from HClO4, which is a strong acid. That cannot act like a base. For here, NaClO3, Na came from NaOH, which is strong. ClO3 minus came from HClO3, which is a weak acid. So this can actually act like a base. HCl is a strong acid, so they just threw that one in there just to mess with you. Okay. For magnesium chloride, magnesium came from magnesium hydroxide, which is a weak base, so this can actually act as an acid, while Cl minus came from HCl, which is a strong acid, so that cannot act like a base. Okay. So for ClO minus, ClO3 minus, if I wanted to write it out, it would be a base dissociation reaction if I wanted to figure out its pH. Okay. So really quickly, I realized I didn't actually answer these questions. So it says, which has the lowest pH? Well, whatever acts as an acid is going to have the lowest pH. And so this guy right here, NH4Br, is going to have the lowest pH. For this question, which has the lowest pH, if you look at it, because this was a trick question, and HCl is actually a strong acid, that will actually have your lowest pH. Okay. For number 6, it tells you, if we are told that a solution is saturated, what is the significance of that? The significance of that is the fact that this is an equilibrium. So if I said, hey, I've got a saturated solution, and the concentration of its ions, let's say, for example, I have a saturated solution of NaCl. And the concentration of sodium ions and chloride ions, I'm just making this up, is 1 molar when it's saturated. Okay? Now, I could have 50 mils of NaCl. I could have 100 mils of NaCl. If both of those are saturated solutions, the concentration of the ions will be 1 molar. No matter how much I start with, right? No matter what volume I have, if it is saturated, I know its concentration always. Even if I just have a drop, it'll be 1 molar. If I have gallons of it, it'll be 1 molar because it is an equilibrium. Now, what happens if you remove that water? So let's say, for example, I have a saturated solution. It's in equilibrium. It's very happy. And I remove water. If you're removing water, logic tells you, since I'm removing water, but it has to keep this concentration, what would have to happen for it to maintain this concentration if you lose water? Well, solid would have to form because you have now extra ions because you lost water. So a solid would form. Another way of thinking of that is if you remove water, you are going to shift to the side with fewer moles of ions. So you're actually going to shift, because if you add water, you're going to shift to the side with more moles of ions. So you're going to actually shift to the left, causing more solid to form. Okay? But common sense tells you if you lose water, but you have to maintain a certain concentration, to maintain that concentration, you're going to have solid forming. Well, what happens if I add water to the solution? Well, if I add water to the solution, I will not be in equilibrium. I will not have a saturated solution until I can actually dissolve more of the solid back into ions, until it can go back and reach this 1 molar saturated solution status. Okay, so if you add water and you have solid present, more of it will dissolve until it reaches that saturated concentration. If you remove water, you're going to end up having solid forming at the bottom because you can only have a 1 molar solution. More cannot be dissolved, so it'll just leave the solution and become a solid. How can we change the pH of a solution? Okay, so this was talking about, I was saying, hey, I've got this pH and I want to change it to a pH of 3. How would you do that? Well, keep in mind, pH is just a measure of the concentration of HCl. So this is really just a dilution problem. Okay? Remember, your pH is the negative log of your concentration of H+. Okay? So to figure out what the concentration of a pH of 1 would be, remember this is base 10. So it's going to be 10 raised to the negative first is my concentration, right? Which means for a pH of 3, my concentration is 10 to the negative third. So since I know the volume of that guy, I want to figure out how I would create a solution that has a lower concentration. So because I'm diluting, yes, I get to use M1V1 equals M2V2. My initial concentration is 10 to the negative first. Its volume is 1 mil. The new concentration is 10 to the negative third. And I'm solving to figure out what volume I would have to end up getting, right, in order to have a concentration of 10 to the negative third. Well, when you solve that, your V2 is going to be 100 mils. So just like any other dilution problem, I'm going to add 1 milliliter of a solution that has a concentration of 10 to the negative first. And I'm going to add enough water until I get a final volume of 100 mils. Now it says how many liters, or I would say milliliters is a better question, of distilled water must be added. Remember, if you add exactly 99 mils, 1 and 99 don't add up to 100 when you're adding water to a solution. So I would just say add enough water until your final volume is 100 mils. Okay, so a basic math, but making sure you really understand what pH means. It is simply a way of taking very small values like 10 to the negative first and 10 to the negative third, or even smaller than that, those concentrations, and making them more manageable. For number 8, how can you use KSP to determine the concentration of ions in solution? So we've already kind of looked at this, right? We're assuming, if I'm dealing with KSP and asking for the concentration, we're assuming that I'm in equilibrium. And so what I can do, I'm going to write out my dissociation reaction. If I'm in equilibrium, I'm going to write my KSP expression. So my KSP in this problem is 3 times 10 to the negative 11. Okay. Then it's going to be x times 3x, but I have to cube it. And so when I solve for this, the x value that I get is 0.001027 molar. And so my concentration of OH minus would therefore just be 3 times that. So what this is telling me is, hey, when I have a saturated solution, because I'm now in equilibrium, it's saturated, the concentration of hydroxide ions would be 0.003. The concentration of aluminum ions would be 0.001. Now, how does KSP tell you, or what does it tell you really about the solubility or the ability of a solid to dissolve? If you think about it, the larger your KSP value, right, the larger the solubility, which makes sense because remember, the larger this value is here, the larger your x value will be, okay? So for the problem that this came from, this is actually a multiple choice question, which is awesome because now one of the silver linings that I don't think you guys have realized is since you don't have multiple choice, you get a calculator. So you can do all these calculations and not have to try and do a lot of the mental math in your head, which makes your life a lot easier. Okay. Number 9, I'm just going to go through quickly. You write down your notes, but I'm not going to write anything. Why don't inert gases affect equilibrium? We're assuming when we're adding an inert gas, number one, we're assuming it's not going to change the pressure at all because you're not adding enough to actually affect pressure. And the reason why they say inert gas, and we're specifically talking about noble gases, they aren't going to react with anything, right? So they're not going to remove anything from your solution. They're not going to react at all, and therefore they are not going to change anything, and therefore won't affect equilibrium. So that's why they don't affect equilibrium. Don't change pressure, and they're not going to react with anything. All right. For 10, someone asked, when do we justify shifts using Le Chatelier's principle versus Q and K? Ultimately, this is the best way to explain anything. Okay? You'll see in answers that they talk about Le Chatelier's principle. You don't ever have to reference Le Chatelier's principle. So if I want to say something shifts to the right, instead of saying it shifts to the right, I would say it proceeds to the products. And the reason why is because Q is going to be less than K. That's why it shifts, in order to make Q big enough so that it can reach K. That's why it shifts to the products. Q is too small. It has to go to the products so that Q can equal K, and you can go back to being in equilibrium. If you're shifting to the right, you would say it proceeds to the reactants. And the reason why is because Q is too big. Q is greater than K. So ultimately, in a lot of answers we've seen, they talk about Le Chatelier's principle, but we officially were told not to teach that and to use Q and K. So if you get stuck and want to talk about Le Chatelier's principle, that's fine, but ultimately Q and K, a comparison is better. All right. I was asked to go over titration curves, and so I'm going to do that. So I'm going to show 3 different possible titration curves. The first is if I have a weak acid being titrated with a strong base. So I'm adding hydroxide, and I start off with just acetate ions. Or sorry, not acetate ions. I start off with just acetic acid. So I'm going to show 4 different steps for each of these problems. So from here on is step 4. Okay. So when I start off here, the only thing that I have present is going to be my acetic acid, because I haven't added any hydroxide yet. Okay, that's step 1. For step 2, I have slowly started adding hydroxide, and I'm going to say this is my half equivalence point. So I've added half as much hydroxide as is needed to reach my equivalence point, which means if I've added half as much strong base as weak acid, that tells me I am at my half equivalence point. And remember, your half equivalence point, which is where pH equals pKa, your concentration of your weak acid and strong base are the same. You have the same concentrations. You've got equal amounts of them. Okay, so at 2, I've got equal amounts of my weak acid and its weak conjugate base, which means between 1 and 2, I actually have more of my acetic acid. Between step 2 and 3, I've actually got more of my conjugate base. Right, so more conjugate base is going to be here in that area, more weak acid is going to be there. As soon as I hit step 3, though, I've added equal amounts of weak acid and weak base. And so the only thing that's going to be present is my acetate ion, which is why the pH at my equivalence point is actually going to be greater than 7, because the only thing that is present at that point, all of the weak acid and all of the strong base are used up because they're equal amounts of them. So the only thing I have present is my weak base. And then from then on, because the only thing that was present was my base, if I keep adding strong base, it's not going to react with anything. It's just going to chill in solution. So the only thing that I'll have that will really affect my pH is hydroxide. Yes, I do have acetate ions, but because I'm just adding OH minus to my acetate ions, the OH is really what's going to affect your pH. Okay. If instead I start with a weak base, NH3, and I add strong acid, my curve is going to look like this. So for step 1, The only thing that is present, because I haven't added H plus yet, the only thing that is present is NH3. As soon as I start adding strong acid, actually, I'm going to go back really quickly. I'm going to really quickly write out this reaction for you to be able to see it. So this is weak acid plus the strong base, which produces your weak base and its water, right? Which is why you start off with just this. Then as soon as I've added half as much hydroxide, I'm going to have just my weak acid and weak base. Then at equivalence point, when I have equal amounts of these, I'm only going to have my weak base. And then if I keep adding hydroxide, I'll have hydroxide and yes, some acetate ions, but really the hydroxide is what affects it. For NH3, this is the reaction. So I only have NH3 present at the beginning. Then as soon as I've added half as much strong acid as I have weak base, then I'm going to have NH3 still present, and I'm going to have its conjugate acid, and I'm going to have equal amounts of those because I'm at my half equivalence point. Half equivalence point, pH equals pKa. Then at my equivalence point, when I've added equal amounts of NH3 and H+, the only thing that's going to be present, neither of these is going to be present. They're going to have reacted completely, so I only have an H4 plus present. And then if I keep going past here, I'm just adding H plus to the NH4 plus because I ran out of NH3 completely. So the only thing that's going to really affect my pH is my H plus concentration. Let's look at the next one. I'm adding strong acid and strong base. So this one's a little bit wonky. So let's say I'm adding strong base to my strong acid. Okay. If I'm at 0.1, I haven't added any hydroxide, so the only thing that's present is H+. And really quickly, I'm going to write out my reaction. Okay. At my, I'm going to put in quotes, half equivalence point. I don't really have a half equivalence point because I don't really have a conjugate here because they're both strong. I've added half as much hydroxide as I had H+. So the only thing that's going to be present is going to be my H+ still, and then some water that formed. So it's not really a half equivalence point because, I mean it is, but I don't have any weak base there. Okay, step 3, I'm at my equivalence point, so equal amounts of these, so neither of them is present, so the only thing I have present is H2O. And then as soon as I've passed my equivalence point, I just keep adding hydroxide. So hydroxide is the only thing that's present. So really quickly to talk about pH, when I'm at my equivalence point with a strong acid and a strong base, because water is the only thing that's present, my pH is 7. While for up here, because I only had NH4 present, NH4 plus present, that is an acid, so my pH will be less than 7. Okay? For number 12, it says, when writing the steps of how to make a solution, do we always need to add some water before the stock solution? So when I was explaining how to properly make solutions, right, I had said in the videos that the best thing is first to add a little bit of water, then to add however much of your stock solution you need, and then to fill up the rest of the way with water to your final volume. The reason why is because by already having a little bit of water, you automatically dilute the stock solution, because if you just start with stock solution and then add water, there's the possibility that you're going to splash yourself. To answer your question, if you remember it, yes, please say add a little bit of water, then add that whatever certain amount of stock solution you need, and then fill it up to the final volume. If you forget, I can't imagine them taking off points for that. Okay. For 13, how can we compare the strength of acids? So there are a number of different ways to do that. The first are the two most obvious ways. So we can compare the pH and the pH of two different solutions, or the Ka, right? So if you compare two solutions that have the same concentration, the one with the lower pH is going to be the one that's stronger. Or the acid that has the larger Ka value is going to be the one that is stronger. Those are the two most obvious ones. Then we get into some slightly trickier ones. So if you look at the table here, I give you 3 different acids. And so obviously, looking here, acid B is going to be stronger than acid A because they have the same concentration, but the pH of acid B is lower. So that tells me it's a stronger acid. But what about for B versus C? They have the same pH. Well, if you think about it, in order for B to have a pH of 2, I need 3 molar of it. While for C, in order for it to have the same pH, you only need 1 molar of it. So you need less of acid C to have that pH, that low of a pH. So since I need less of C, that means C is going to be a stronger acid. So if you have the same pH, okay, the acid that requires a lower concentration will be stronger. Okay. Well, there's another situation where we're asked to compare the strength of acids and bases, and that's this one. So this has come up multiple times, and it just freaks you guys out, so let's talk about it. All right, so here's an acid-base reaction. If my K is much larger than 1, what that tells me is that my products are favored. Well, if my products are favored, that means that these 2 substances did a really good job of reacting in order to form those products, which tells me if I'm comparing HA versus HB, since HA did such a good job reacting, that tells me that HA is a stronger acid. Okay, so if your products are favored, okay, then the acid that is a reactant is stronger than the acid that was a product. Same thing applies for a base. Since your products are favored, that means B- did a better job of reacting than A- did. If the reverse is true, if your K is less than 1, what that tells you is that your reactants are favored, meaning HB and A- did a better job of reacting to form your reactants, which would mean HB would be stronger than HA as far as acids are concerned, and A- would be stronger as far as products are concerned. Okay. For 14, can you explain percent ionization again and how to increase it? So remember, your percent ionization is simply going to be your X, your change, whatever it is, divided by the initial concentration of your reactant. So for this problem, and then we're going to multiply by 100. So for this problem, my X is going to be either my concentration of H3O plus or A minus, one of those. So let's just say it's H3O plus, divided by the initial concentration of HA. And then I'm going to multiply by 100. Well, how do I maximize the amount of H3O plus or A minus that's formed? Well, I'm going to want to shift to the right to form more product. Now, there are a couple of different ways I can do that. And the 2 that were studied for this problem was I could either add water, which would cause a shift to the right, or I could add HA, which would cause a shift to the right. The issue with HA, water works perfectly fine. The issue with HA is because HA is causing a shift to the right, that's great for H3O+. But by adding extra initial HA, that's going to cause the value on the bottom to also increase. So while it increases H3O+ concentration, it also increases the concentration of HA, which is an issue because when you divide by 2 values that have both been made larger, it's going to cause the percent ionization to not increase as much. If you added just water, it would cause H3O+ to increase. It wouldn't affect the initial concentration of HA, causing the percent ionization to be larger. All right, there are questions about how to determine the pH of a buffer. Okay, so really quickly, if we have an ideal buffer, meaning an ideal buffer is when you have an equal amount of weak acid and weak base, then when I'm using my Henderson-Hasselbalch equation, since my concentration of my base and my acid are the same, this value is going to be 1. The log of 1 is actually 0. So that's why my pH actually equals my pKa when I have an ideal buffer. But I haven't actually said I have an ideal buffer. And so instead, I might actually have to use this entire formula. The reason why finding the pH of a buffer is really easy is because by definition, a buffer consists of a weak acid and a weak base. As soon as you have a weak acid and a weak base, referencing back that first problem that we worked on, as soon as I have a weak acid and a weak base, I know I can use my Henderson-Hasselbalch equation to solve that. And so all I have to do is then say, okay, pH equals pKa plus the log of my base over my acid. Okay, I know my moles of my acid. I know my moles of my base. Keep in mind here, this C2H5COO minus is my base. They just switched the order of this. Don't let that freak you out. The Na came from a strong base. That's why I ignore it. Okay, and I know my initial volume. So I can figure out the concentration of each of these and plug them in. Of my Ka value, which was given to me, the concentration of my base is just going to be 0.1 divided by 1.20, which is 0.0833. And then for my concentration of my acid, divide that, and I get 0.125. And so you can easily figure out the pH, which will be, I actually didn't calculate it, funnily enough. So you can figure that out. I wanted to add, no one asked about this, but I noticed a lot of people were having issues with taking a buffer and then adding either a strong base or a strong acid to it. So if I add a strong base, OH minus, to a buffer, remember the buffer consists of the weak acid, C2H5COOH, and the weak base, C2H5COO minus. Remember, strong bases only react with weak acids. If instead I were adding a strong acid, only adding a strong acid, it would react with a weak base. Okay, so here, because I'm adding a strong base to a weak acid, I'm going to write out this reaction. It's going to react completely to form the weak base and water. Okay, so the weak acid reacted with a strong base. If it asks me now to calculate my pH, what I need to do is I need to figure out the initial concentrations of everything. Well, I know my initial concentration of my weak acid. We plugged it in before, 0.125, because we got it by dividing. I know my concentration of my strong base, 0.001 divided by 1.2, and I get 0.00833. Now the one place where everyone messes up, remember you do have a buffer here, so you have a weak base present. It's not 0. You actually have weak base. So I know its concentration is 0.0833. And this is super important, okay? If I then decided, hey, I'm going to add a strong acid, this could react with a strong acid. So don't forget to include the initial concentration of that. Then, because this is a strong base, it's going to react completely. Plus, for this side, it's 2 zeros. I dropped a 0. Sorry about that. Okay, so now I know the equilibrium concentrations. Okay, which leads to the question of, okay, well now what do I do? How do I figure out the pH? Well, good news, I've got weak acid and weak base present, so when I have both of them present, I can just use my Henderson-Hasselbalch equation. This is my concentration of my base. This is the concentration of my acid, so the pH that I get is 4.10. Okay, 2 quick last questions. Without a calculator, determine the pH range this solution would have in HCl. Okay, so what range of pHs could this have? Keep in mind, this problem is made a lot easier because this is a strong acid. If this were not a strong acid, if this were a weak acid, you would have to create an ice chart. This would be your initial concentration. Then you'd subtract X, add X, add X, and figure it out numerically. You'd actually have to calculate it out with a calculator. But because you have a strong acid, I know all of this is going to dissociate. Okay? So since all of it dissociates, this is going to be the concentration of H plus in solution. So this, to determine the range, since that is the concentration of H plus, this value is going to be less than 10 to the negative fifth, because remember, it's going to be somewhere between 10 to the negative fifth. It's less than that because the negative 5, this makes it less than that. This is going to be greater than 10 to the negative 6. So to figure out the pH of that, you've got 6 and 5. So your pH is going to be greater than 5, but less than 6. Because keep in mind, you got to switch these values because otherwise it doesn't make sense for the pH to be less than 5, but greater than 6. So you got to switch those. And then for the last one, how does changing the pH affect solubility? Okay, so if I were to show this dissociating, okay, remember, if this is shifting to the right, that would increase the solubility because we're saying that HCl is a solid here. So if I'm shifting to the right and I'm forming more ions, I want this to decrease, because if that decreases, that would cause a shift to the right to increase my solubility. And so to increase my solubility, I would need to increase pH. And so there are two ways I could do that. Because if I decrease pH, keep in mind, H plus concentration decreases. So I could either remove H plus by having it react with something, or ultimately the same thing, if I added OH minus, that would cause my concentration of H plus to decrease, which would then cause my solubility to increase. For here, very similar. I want it to shift to the right to increase my solubility, so how would I do that? Well, I want this concentration to decrease. So I'm going to want my pH to decrease now if I want my concentration of OH minus to decrease. So I could either add, I could add H plus. By adding H plus, that removes OH minus because it forms water. The other thing for OH minus that I could do is I could actually add an ion, like for example, silver, that could form a precipitate with it. By adding a precipitate, I decrease the concentration of hydroxide, causing a shift to the right. So keep in mind, how would changing pH affect it? Well, if I have H plus and I want to decrease the concentration, by decreasing the concentration of H plus, what I'm really wanting to do is increase the pH. While for here, to decrease the concentration of OH minus, what I'm really wanting to do is to decrease the pH. And the ways that I do that, I could add OH minus to remove it, and that would increase the pH, or I could add H plus, or I could add anything that forms some sort of a precipitate to remove the OH minus.